The relational model for database management is an approach to managing data using a structure and language consistent with first-order predicate logic, first described in 1969 by Edgar F.Codd. In the relational model of a database, all data is represented in terms of tuples, grouped into relations. A database organized in terms of the relational model is a relational database. The purpose of the relational model is to provide a declarative method for specifying data and queries. Users directly state what information the database contains and what information they want from it, and let the database management system software take care of describing data structures for storing the data and retrieval procedures for answering queries. Most relational databases use the SQL data definition and query language. These systems implement what can be regarded as an engineering approximation to the relational model. A table in an SQL database schema corresponds to a predicate variable, the contents of a table to a relation, key constraints, other constraints, and SQL queries correspond to predicates. However, SQL databases deviate from the relational model in many details, and Codd fiercely argued against deviations that compromise the original principles. Overview. The relational model's central idea is to describe a database as a collection of predicates over a finite set of predicate variables, describing constraints on the possible values and combinations of values. The content of the database at any given time is a finite model of the database, i.e., a set of relations, one per predicate variable, such that all predicates are satisfied. A request for information from the database is also a predicate. Alternatives. Other models are the hierarchical model and network model. Some systems using these older architectures are still in use today in data centers with high data volume needs, or where existing systems are so complex and abstract it would be cost-prohibitive to migrate to systems employing the relational model. Also of note, are newer object-oriented databases. Implementation. There have been several attempts to produce a true implementation of the relational database model as originally defined by Codd and explained by Darwin and others, but none have been popular successes so far. As of October 2015, update, REL is one of the more recent attempts to do this. The relational model was the first database model to be described in formal mathematical terms. Hierarchical and network databases existed before relational databases, but their specifications were relatively informal. After the relational model was defined, there were many attempts to compare and contrast the different models, and this led to the emergence of more rigorous descriptions of the earlier models, though the procedural nature of the data manipulation interfaces for hierarchical and network databases limited the scope for formalization. History. The relational model was invented by E.F. Codd as a general model of data, and subsequently maintained and developed by Chris Date and Hugh Darwin among others. In the third manifesto, Date and Darwin show how the relational model can accommodate certain desired object-oriented features. Controversies. Codd himself, some years after publication of his 1970 model, proposed a three-valued logic version of it to deal with missing information, and in his The Relational Model for Database Management version 2 he went a step further with a four-valued logic version. But these have never been implemented, presumably because of attending complexity. SQL's null construct was intended to be part of a three-valued logic system, but fell short of that due to logical errors in the standard and in its implementations. Topics. The fundamental assumption of the relational model is that all data is represented as mathematical NARY relations, an NARY relation being a subset of the Cartesian product of n domains. In the mathematical model, reasoning about such data is done in two-valued predicate logic, meaning there are two possible evaluations for each proposition, either true or false. Data are operated upon by means of a relational calculus or relational algebra, these being equivalent in expressive power. The relational model of data permits the database designer to create a consistent, logical representation of information. Consistency is achieved by including declared constraints in the database design, which is usually referred to as the logical schema. The theory includes a process of database normalization whereby a design with certain desirable properties can be selected from a set of logically equivalent alternatives. The access plans and other implementation and operation details are handled by the DBMS engine, and are not reflected in the logical model. This contrasts with common practice for SQL DBMSs, in which performance tuning often requires changes to the logical model. The basic relational building block is the domain or data type, usually abbreviated nowadays to type. A tuple is an ordered set of attribute values. An attribute is an ordered pair of attribute name and type name. An attribute value is a specific valid value for the type of the attribute. This can be either a scalar value or a more complex type. A relation consists of a heading and a body. A heading is a set of attributes. A body is a set of n tuples. The heading of the relation is also the heading of each of its tuples. A relation is defined as a set of n tuples. In both mathematics and the relational database model, a set is an unordered collection of unique, non-duplicated items. Although some DBMSs impose an order to their data, in mathematics, a tuple has an order, and allows for duplication. F.Codd originally defined tuples using this mathematical definition. Later, it was one of E.F.Codd's great insights that using attribute names instead of an ordering would be so much more convenient in a computer language based on relations. This insight is still being used today. Though the concept has changed, the name tuple has not. An immediate and important consequence of this distinguishing feature is that in the relational model the Cartesian product becomes commutative. A table is an accepted visual representation of a relation. A tuple is similar to the concept of a row. A real var is a named variable of some specific relation type, to which at all times some relation of that type is assigned, though the relation may contain 0 tuples. The basic principle of the relational model is the information principle. All information is represented by data values in relations. In accordance with this principle, a relational database is a set of real vars and the result of every query is presented as a relation. The consistency of a relational database is enforced, not by rules built into the applications that use it, but rather by constraints declared as part of the logical schema and enforced by the DBMS for all applications. In general, constraints are expressed using relational comparison operators, of which just one is theoretically sufficient. In practice, several useful shorthands are expected to be available, of which the most important are candidate key and foreign key constraints. Interpretation. To fully appreciate the relational model of data, it is essential to understand the intended interpretation of a relation. The body of a relation is sometimes called its extension. This is because it is to be interpreted as a representation of the extension of some predicate, this being the set of true propositions that can be formed by replacing each free variable in that predicate by a name. There is a one-to-one correspondence between the free variables of the predicate and the attribute names of the relation heading. Each tuple of the relation body provides attribute values to instantiate the predicate by substituting each of its free variables. The result is a proposition that is deemed, on account of the appearance of the tuple in the relation body, to be true. Contrariwise, every tuple whose heading conforms to that of the relation, but which does not appear in the body, is deemed to be false. This assumption is known as the closed-world assumption. It is often violated in practical databases, where the absence of a tuple might mean that the truth of the corresponding proposition is unknown. For example, the absence of the tuple from a table of language skills cannot necessarily be taken as evidence that John does not speak Spanish. For a formal exposition of these ideas, see the section Set Theoretic Formulation below. Application to databases. A data type as used in a typical relational database might be the set of integers, the set of character strings, the set of dates, or the two Boolean values true and false, and so on. The corresponding type names for these types might be the strings, int, char, date, Boolean, etc. It is important to understand, though, that relational theory does not dictate what types are to be supported. Indeed, nowadays provisions are expected to be available for user-defined types in addition to the built-in ones provided by the system. Attribute is the term used in the theory for what is commonly referred to as a column. Similarly, table is commonly used in place of the theoretical term relation. A table data structure is specified as a list of column definitions, each of which specifies a unique column name and the type of the values that are permitted for that column. An attribute value is the entry in a specific column and row, such as John Doe or 35. A tuple is basically the same thing as a row, except in an SQL DBMS, where the column values in a row are ordered. An attribute name might be name or age. A relation is a table structure or definition along with the data appearing in that structure. The structure or definition is the heading and the data appearing in it is the body, a set of rows. A database relva is commonly known as a base table. The heading of its assigned value at any time is as specified in the table declaration, and its body is that most recently assigned to it by invoking some update operator. The heading and body of the table resulting from evaluation of some query are determined by the definitions of the operators used in the expression of that query. SQL and the relational model. SQL, initially pushed as the standard language for relational databases, deviates from the relational model in several places. The current ISO SQL standard doesn't mention the relational model or use relational terms or concepts. However, it is possible to create a database conforming to the relational model using SQL if one does not use certain SQL features. The following deviations from the relational model have been noted in SQL. Note that few database servers implement the entire SQL standard and in particular do not allow some of these deviations, whereas null is ubiquitous. For example, allowing duplicate column names within a table or anonymous columns is uncommon. Duplicate rows. The same row can appear more than once in an SQL table. The same tuple cannot appear more than once in a relation. Anonymous columns. A column in an SQL table can be unnamed and thus unable to be referenced in expressions. The relational model requires every attribute to be named and referenceable. Duplicate column names. Two or more columns of the same SQL table can have the same name and therefore cannot be referenced. On account of the obvious ambiguity, the relational model requires every attribute to be referenceable. Column order. Significance. The order of columns in an SQL table is defined and significant. One consequence being that SQL's implementations of Cartesian product and union are both non-commutative. The relational model requires there to be no significance to any ordering of the attributes of a relation. Views without check option. Updates to a view defined without check option can be accepted, but the resulting update of the database does not necessarily have the expressed effect on its target. For example, an invocation of insert can be accepted but the inserted rows might not all appear in the view, or an invocation of update can result in rows disappearing from the view. The relational model requires updates to a view to have the same effect as if the view were a base relva. Column-less tables. Unrecognized SQL requires every table to have at least one column. But there are two relations of degree 0 and they are needed to represent extensions of predicates that contain no free variables. Null. This special mark can appear instead of a value wherever a value can appear in SQL, in particular in place of a column value in some row. The deviation from the relational model arises from the fact that the implementation of this ad hoc concept in SQL involves the use of three-valued logic, under which the comparison of null with itself does not yield true but instead yields the third truth value, unknown. Similarly, the comparison null with something other than itself does not yield false but instead yields unknown. It is because of this behavior in comparisons that null is described as a mark rather than a value. The relational model depends on the law of excluded middle, under which anything that is not true is false and anything that is not false is true. It also requires every tuple in a relation body to have a value for every attribute of that relation. This particular deviation is disputed by some if only because E. F. Codd himself eventually advocated the use of special marks under four-valued logic. But this was based on his observation that there are two distinct reasons why one might want to use a special mark in place of a value, which led opponents of the use of such logics to discover more distinct reasons, and at least as many as 19 have been noted, which would require a 21-valued logic. SQL itself uses null for several purposes other than to represent value unknown. For example, the sum of the empty set is null, meaning 0, the average of the empty set is null, meaning undefined, and null appearing in the result of a left join can mean no value because there is no matching row in the right-hand operand. Relational operations users request data from a relational database by sending it a query that is written in a special language, usually a dialect of SQL. Although SQL was originally intended for end users, it is much more common for SQL queries to be embedded into software that provides an easier user interface. Many websites, such as Wikipedia, perform SQL queries when generating pages. In response to a query, the database returns a results set, which is just a list of rows containing the answers. The simplest query is just to return all the rows from a table, but more often, the rows are filtered in some way to return just the answer wanted. Often, data from multiple tables are combined into one, by doing a join. Conceptually, this is done by taking all possible combinations of rows, and then filtering out everything except the answer. In practice, relational database management systems rewrite queries to perform faster, using a variety of techniques. There are a number of relational operations in addition to join. These include project, restrict, union, difference, intersect, and product. Depending on which other sources you consult, there are a number of other operators, many of which can be defined in terms of those listed above. These include semi-join, outer operators such as outer join and outer union, and various forms of division. Then there are operators to rename columns, and summarizing or aggregating operators, and if you permit relation values as attributes, then operators such as group and ungroup. The select statement in SQL serves to handle all of these except for the group and ungroup operators. The flexibility of relational databases allows programmers to write queries that were not anticipated by the database designers. As a result, relational databases can be used by multiple applications in ways the original designers did not foresee, which is especially important for databases that might be used for a long time. This has made the idea and implementation of relational databases very popular with businesses. Database normalization relations are classified based upon the types of anomalies to which they're vulnerable. A database that's in the first normal form is vulnerable to all types of anomalies, while a database that's in the domain key normal form has no modification anomalies. Normal forms are hierarchical in nature. That is, the lowest level is the first normal form, and the database cannot meet the requirements for higher-level normal forms without first having met all the requirements of the lesser normal forms.